Welcome back, everyone. Welcome back to our enlightening lecture series on non-smooth optimization in infinite dimensional spaces. If you find yourself watching this video, you are likely a passionate math enthusiast eager to elevate your understanding of mathematics to new heights. So I therefore wholeheartedly encourage you to subscribe to my channel, right, for a continuous journey of intellectual growth. Keep in mind that subscribing is not just about staying updated, but also about becoming part of a vibrant mathematical community dedicated to pushing the boundaries of mathematical knowledge. So don't miss out on the opportunity to sharpen your mathematical skills, and I hope you will hit the subscribe button, right, and become a valued member of our ever-growing community. So in this video, we are going to study the symbiotic relationship between Caratheodory functions and Nemytskii operators, right? Nemytskii operators are also known as superposition operators, right? Those are operators that typically arise from pointwise application of a real valued function. So, but don't worry, I'll be getting to that, right? So, one step at a time. So, let's begin by acquainting ourselves with Nemytskii operator. So, let's have a definition. So definition. Okay, so let omega might be subset of Rn, be open and bounded. Right, and say we have P and Q in 1 plus infinity. Right, now consider a function little f, right, defined on the Cartesian product omega cross R into R, right? Then the corresponding superposition, so the corresponding let me put it in color. I think I have to choose this color here. The corresponding superposition or Nemytskii operator. Nemytskii was actually a mathematician, right? And he's actually at the origin of superposition operators. I think he was a Russian mathematician, by the way. So the corresponding superposition or Nemytskii operator, right, is given by it's actually defined, we define it as capital F, right? Defined from LP of omega into LQ of omega, right? Defined by f of u applied to x, right? Because f of u is an element of LQ of omega, so it maps the element of omega into R. So capital F of u of x, is equal to little f at x comma u of x, right? For let me just write it down here, for almost every x in omega, of course. So let me quickly highlight the assumption of the definition. So we need omega should be open and bounded, right? And here P and Q, right? They in 1 plus infinity. Okay, so if you have a function little f, right? So the corresponding superposition operator is the function capital F here, right? Defined this way for almost every x in omega. So f actually takes element in LP, right? In LP of omega, right? And maps it to a function LQ of omega. So this function here should be in LQ of omega. So of course, yet the elegance of Nemytskii operator is of course accompanied by conditions, right? Because I said that this element should be in LP of omega, so it should be Q integrable, and we also need sort of measurability, right? So for this operator f, capital F, right, to be well defined, we need certain restrictions on little f, right? So I will just write so it's given by capital F such that the following hold. So the first thing we will require is that our function little f should be a Caratheodory function. And then I will tell you what it is. F is a Caratheodory. It's a Caratheodory function. Let me just write it here. Oops. So this means that, I mean, for little f to be a Caratheodory function, f should fulfill, let's call it 1. So I think let me probably use another color, like yeah, it would be great. So for every z in R, right, I mean, if you fix the second component of the function little f, then the mapping which at x associate f of x comma z should be measurable. Right, so I mean, so this means that, I mean, if you view little f as a function of x, right, so this should be measurable. Right? So this is another way of writing that. Okay, so we also need the second condition, right, for the function to be the Caratheodory function. For every x, now if you fix x in omega, right, then the mapping which at z associate f of x comma z, right, is continuous. So if you view f as a function of z, then the map should be continuous. Okay, well, f is a Caratheodory function, so that means little f as a function of x is measurable and as a function of z is continuous. But this alone is not, I mean, it's not enough, right, to ensure that this alone is not enough to ensure that our function f is actually, I mean, it's well defined, right? Because in fact, f being a Caratheodory function only ensures that the Nemytskii operator, I mean, or the superposition operator, applied to an element u in LP of omega is measurable, right? So we need also that fu, I mean, capital F of u, right, to be Q integrable, right? So we need Q integrability of capital F of u, right? Because this should be in LQ. Okay, so we need, so we additionally require the following Roth condition. Oops. So additionally, we require the Roth condition. So let's go to Roth condition. So for given P and Q, now in 1 plus infinity, we exclude plus infinity. I'll tell you why in a second. So there exists, oops, this looks ugly. So there exists A, right, in LQ of omega, right? And there exists also B in L infinity of omega, such that, oops, such that the absolute value of f of x comma z, right, is less or equal than a of x plus b of x times the absolute value of z to the power p over q, right? Okay, so let's call this growth condition G, right? So we use it. Again, let me just highlight the fact that we need P and Q to be 1 plus infinity, right? I mean, if you use the convention that probably I will not write it down. So you can still define, I mean, this growth condition, right? If P is actually less than infinity and Q is plus infinity, right? And also if P is but if P is actually plus infinity and Q is actually less than plus infinity, you have an issue, right? So, okay, so, I mean, this growth condition is kind of, I think it's kind of weaker, right? Because we can actually require that F is actually in LQ, right? But this is stronger, right? So, but this growth condition, growth condition is a weaker condition, right? Because weaker in the sense that, I mean, if this growth condition hold, if this growth condition hold, this condition here, then I'm sure that F is actually in LQ of omega, right? I mean, because this part here is actually in LQ, because remember our domain omega is open and bounded, right? So this element will be in LQ of omega. Yeah, given that this is in LQ and this is in L infinity, right? And this to the power P over Q is actually in LQ, of course, right? So remark, so this is how we will define the Nemytskii operator or superposition operator. So now let's have a remark. So so the growth condition, this growth condition G here do not only contribute to the well-definedness, to the well-definedness of of the Nemytskii operator, right? But they also contribute to the continuity of our superposition operator. So this is, so let me use another color. So the growth condition. So the growth condition G not only contributes to the well-posedness or probably I use well-posedness. No, I think, well, let me keep on well-definedness. Now, yeah, probably let me keep well-posedness. So the growth function do not only contribute to the well-posedness of our Nemytskii operator, but also contribute to the continuity of our superposition operator. Oops. So let me just highlight the key point: continuity of our superposition operator F, writing this growth condition here. Okay, so this result is actually entailing the following theorem that we are going to prove. So this will be theorem 2.10. So if the Caratheodory function little f, right? Define omega cross r into r satisfies the growth condition G, right? For, of course, P and Q in 1 plus infinity. I think, let me try to put, yeah. So for P and Q in 1 plus infinity, infinity is excluded. Then the superposition operator the corresponding superposition operator, capital F, right, defined from LP of omega into LQ of omega, right? Maybe define it as Fu of x equals f of x, u of x, right? So let me try to write a bit smaller. First for f of x, comma u of x, right? Oops. For almost every x, right, in omega, of course, is continuous. So let me just highlight some of the key assumptions. So we need our superposition, we need to have first a Caratheodory function, right, that satisfies the growth condition G, right? Of course, now we need P and Q to be between 1 and plus infinity, right? Plus infinity excluded, right? So, so then in this case, the corresponding superposition operator or the Nemytskii operator, right, associated to the function little f is actually continuous. Okay, so let's have a look at the proof. Okay, now since LP of omega is a metric space, right? I mean, we know that sequential continuity is equivalent to continuity, right? When you're actually in metric space, sequential continuity and continuity are just equivalent, right? But in a general topological space, it's a function, continuity is kind of, sequential continuity is stronger, right? Stronger in the sense that continuity will always imply sequential continuity, but sequential continuity may not always imply continuity. Right? So, okay, so because we are in a metric space, right, it's enough for us, it's enough to prove that, it's enough to prove that capital F, right, our corresponding superposition operator is sequentially continuous. So we just need to check for sequential continuity. Okay, so for that, let un, right, be a sequence in LP of omega, right, such that un converges strongly to u, right, in LP of omega, right. So strong convergence here means that, the norm difference, right, goes to 0, right. Okay, good. So our goal is actually to show that the function value, right, f of un converges to f of u, right? So that would be sequential continuity. So let me just write it. So we aim at showing that f of un converges to f of u, right? But remember f of un, or I mean, it's valued in LQ of omega. So we are not showing that this goes to this in LQ of omega. Okay, so of course the way we are going to do this is by, I mean, when you have, I mean, we are in LQ spaces, LP spaces, right? You should always think of, I mean, of the notions that we know from measure theory, right? I mean, Fato's lemma, monotone convergence, dominated convergence theorem. So we are going to achieve this via the use of, well, we write it down, via the use of, let me just use another color. So of dominated convergence theorem. So we will achieve this via the use of the, I mean, just write the shortcut, right, of the dominated convergence theorem, DCT. Okay, so this is the goal. So at least you know already what we are going to do. I mean, where we are going. Since un converges strongly to u in LP of omega, right? Then I mean up to a subsequence. That I'm not going to relabel, right? Un converges to u pointwise, right? I mean almost everywhere. So strong convergence in LP always implies pointwise convergence. So since un converges strongly to u in LP of omega, then up to a subsequence, right? Then up to a subsequence, not explicitly relabeled. Un converges to u, I mean almost everywhere, right? Almost everywhere. So this means that un of x, right, converges to u of x, right, for almost every x in omega, of course, right? I might not write x in omega, but you should know that x lies in omega. Now I'm going to do something, right? So because the aim, I said, we want to use the dominated convergence theorem, so we need to kind of find a function that, I mean, that will dominate, basically f of un, right? That is integrable. So now, probably I use another color. Okay, good. So now observe that if we set Gn, right, to be the summation, the absolute value of uk plus 1 minus uk, right, k moving from 1 to n minus 1, say, right, then, I mean, Gn is positive, right, then, and it's obviously measurable because the uk are measurable, right, they are elements of LP, right, of LP of omega. So Gn is measurable and positive, right, because you have a sum of the absolute value. Then using Fato's lemma, by the way, if you were not, I mean, confident with measure theory, I strongly invite you to watch my lecture series on measure theory, right? I think I did a lecture on measure theory in my functional analysis lecture series. So please check it out. So then using Fato's lemma, let me just squeeze it here, right? I mean, you know, you're going to apply to Gn to the power p, right, which is still greater than 0, right? So using Fato's lemma, we get, I mean, we have that the integral of omega, right, of the limit of Gn to the power p of x, right? When of the lim inf, right? I mean, but it's actually the lim inf. Just write the limit here. So the integral of this plus infinity, right? Dx is less or equal than what? Than the lim inf of the integral of omega of dn to the power p of x dx, right? Of course, when n goes to plus infinity, right? Now, this here is actually less or equal than the lim inf of the norm of dn, the LP norm of this, right, to the power p, right, plus infinity, right? Now, what you do is that we just, so let me just write it probably, so this is less or equal than the lim inf of the integral over omega of the summation, right, over k moving from 1 to n minus 1, because remember gn was the summation, right? So here can use kind of a triangle inequality, right? So to get this inequality here, so this is also equal to the lim inf of the integral of the summation of the absolute value of uk plus 1 minus uk plus 1 of x, right, minus uk of x to the power p dx, right? So you have to shift it a bit to the left, right? And this is everything raised to the power p. Okay, so now what you do is that well, just probably do this, right? Now you shift this out of the integral, right? So you put the sum outside of the integral, and you apply the Minkowski, right? Minkowski inequality. So if you do that, then you get that this is less or equal than the lim inf of the summation k moving from 1 to n minus 1, right, of the norm of u k plus 1 minus uk, the LP norm of this, right, and everything to the power, of course this is in plus infinity, everything to the power p, right? So and now what you can do is actually you can even make n goes to plus, I mean increase the summation, right, up to infinity. So this is also equal to this term here, this LP norm here, right? Of course everything is still raised to the power p. And now one thing that you should observe is that we can even choose this our subsequence in such a way that this norm here is actually less so equal to 1 over 2 to the power k, right? So we can choose a subsequence, right, such that it is less so equal than, you put an arrow on this side, and this is actually finite. Okay, so basically this means, just write it here, so this means that the limit of dn of x, right, is finite, right, for almost every x in omega, right? Because remember we were upper bounded the this integral here, right? So we saw that this is finite, so the limit is finite for almost every x in omega, right? This is of course as n goes to plus infinity, and we also proved that the limit of dn, right, plus infinity, right, is p integrable. Okay, now another thing that you have to see is that the absolute value of un of x, right, is equal to now you can use telescopic sum. So this is again the absolute value of the summation over k moving from 1 to n, right, of uk plus 1 minus uk of x, right, plus uk of x. And this is just by telescopic sum, right? And this is actually less or equal than gn of x, right, if you use triangle inequality, right, plus the absolute value of u1 of x, right? And now this is actually less or equal than the absolute value of the function v of x, right, that is p integrable plus the absolute value of u1 of x. So why is that? Let me just justify this step. This is because the limit of gn, right, gn of x is finite, right, and that it's finite, right, almost everywhere. I mean, for almost every x, right, and that, let me write it probably here, and gn, right, is an increasing sequence of positive functions, right? So there exists a function v in LP such that the term of the sequence are kind of upper bounded by v of x, absolute value of v of x. So what I wanted to, I mean, this was actually kind of a demonstration for something I'm going to state, right? I mean, I didn't want to claim it, right, but show you how we can prove it. So by the way, I said that this is actually LP of omega. So I didn't want just to write the result, right, but show you what are the steps, right? So so from this, right, from this convergence of pointwise convergence of the sequence un to u of x, right, and due to all this step here that we did, right, one can actually conclude that so there exists a function v, right, in LP of omega, right, such that the absolute value of un of x, right, is less or equal than the absolute value of v of x, right, plus absolute value of u1 of x, right? And now what you can do is actually, you can actually call all this term here, you can call it g of x, right? And of course this holds for every n, right, and for almost every x in omega, of course. Okay, so now as the function, I mean, we know that our function is a Caratheodory function, so that means u as a function of z, it is continuous. Now as this map here is continuous, right? Remember f is a Caratheodory function, so it follows that I mean, this in particular sequentially continuous. So you have that f of x comma un of x, right, should converge to f of x comma u of x, right, for almost every x in omega, right? So this means, I mean, if you pass in the integral over omega, right, so then you get that don't need to pass the integral, right, but this is because this is exactly the definition of our superposition operator. So this means f of un of x, right, well, let me just write x here, converges to, this is equal to this, converges to fu of x, right, for almost every x, right? So you have pointwise convergence already of our sequence f of un. Now, our second condition that we need in order to fulfill all the assumptions of the dominated convergence theorem, we need to show that our sequence f of un is actually upper bounded, right, by a function that is L1 integrable. Yeah, I think so. Okay, so moreover, the absolute value of f of un, like applied to x, is equal to the absolute value of f of x, comma un of x, right? Now, using the growth condition, because our function f is a Caratheodory function, so this is, here we use the growth condition. The growth condition, yeah. So this is less or equal than a of x, right? We have the existence of a function a of x in LQ plus b of x times the absolute value of un of x to the power p over q. And this is actually less or equal than a of x, right, plus b of x. But we actually, remember, we actually saw that un of x is actually upper bounded by function d of x, right? You can put it in absolute value if you want. Or p over q, sorry. Right, because we saw that this is actually less or equal than this term here. Okay, so, and this of course hold for almost every x in omega. Now, since the function g is actually in LP, is in LP of omega, right? Then the right hand side, I mean this side here, right? Probably let me just write it again. So this means then this function here plus b dot times the absolute value of g dot to the power p over q, right? This function here is actually in LQ of omega, right? And you can apply the dominated convergence theorem, right? Because I mean our so this is in LQ of omega, and we can apply the Lebesgue dominated convergence theorem, right, to conclude. So let me quickly highlight the best dominated convergence theorem. So we can apply it to conclude that our sequence f of un, right, converges to f of u, right, in LQ of omega. Okay, good. But well, we prove that f of un converges to f of u in LQ of omega, but don't lose sight of the fact that this holds only for a subsequence, right? Yeah, I mean, this only holds for a subsequence. Remember, we move from strong convergence in LP to pointwise convergence, right, up to a subsequence. So, but this is not a big deal, right? I mean, this is not a deal at all, right? Because the argument we use can be applied to any subsequence, and therefore the whole sequence must converge to FU. So let me just write here as this argument. Can be applied to any subsequence of the sequence f of un, to any subsequence of to any subsequence, right? So the whole sequence must converge to FU, right, which yields continuity of F. I mean, this is basically what you probably know or might not know. This is the subsequence argument, right? If you have a sequence, right, for which all the subsequences, right, all subsequence of a sequence converges, right, to a limit, the same limit, then the whole sequence must converge, right, to that same limit, right, due to the uniqueness of the limit, right, and also to converge to the same thing because uniqueness of the limit follows from the fact that the space is actually Hausdorff, right? Hausdorff means that the space is separated, right? In the sense that if you give me two distant points, then I can always find two disjoint neighborhoods of those points. So this is a subsequence argument, right? All subsequences, of a sequence converges to a limit, right? Then the whole sequence must converge to that same limit by uniqueness of the limit. Okay, so while continuity is actually a short for, it's a short when you have a Caratheodory function, the differentiability, right, of the superposition operator is kind of, it's a trickier proposition. In fact, we would like to say that, probably let me just write it here. So now what we want is that, you want to say that, if our Caratheodory function little f, right, is differentiable. So this is what we want to get. Little f differentiable implies capital F differentiable, right? We would like to get this, right? And ideally with pointwise derivative, right? Ideally with pointwise derivative in the sense that f prime of u, right, which will be defined from Lp of omega into Lq of omega, right? Should be should be defined such that f prime of u applied to h at x, right, should be equal to, you want the pointwise thing, so this should be f prime of u of x h of x. But this actually doesn't hold in general, right? So I think I probably forgot an argument, probably x somewhere here, yeah. So but this, let me just write it, but this, this does not hold in general, right? And this is not always true, right? If you have, we don't always have this thing, right? To convince yourself, you can think of, just write it for example, to convince yourself. For example, you can actually consider the function little f, right, defined from omega cross r into r, which maps xz, right, to the sine of z, right? This is the sine function, right? So if you have this function here, which is obviously a Caratheodory function, then the corresponding superposition operator, then the corresponding superposition operator will be the function capital F, right, defined from, Lp of omega into, now I chose the codomain to also be LP of omega intentionally, right, with P in 1 plus infinity. So let me just highlight this on this side. So, and P is in 1 plus infinity, right? So the superposition operator is actually defined by Fu of x, right? It's equal to the sine of U of x. But this superposition operator is not differentiable, right? I mean, this is what I put it in column. It's not differentiable in U equal to 0, right? For the simple reason that I mean, this you can actually check, right? It's not difficult, very easy. For the simple reason that the pointwise product of the derivative of sine of U, right, at U equal to 0, oops, and a direction H in LP of omega, right? I mean, this might not be well defined, right? I mean, what I mean is that F prime at 0, right, in the direction H, right, may not be well behave in LP of omega, right? So this might not be, right, this so this might not be an element of LP of omega. I mean, remember our codomain was still LP of omega, right? And again, a warning. So I said P was actually between 1 and plus infinity, right? So it is important to stress that fact out. Warning, in this example, I mean the above example, P is actually between 1 and plus infinity, right? Plus infinity is excluded, right? For the simple reason that, I mean, for we use this color, for P equal infinity, right? One can prove one can show that the map, right, which at U associate sine of U, right, is Fréchet differentiable, right? Is Fréchet can show that this map is Fréchet differentiable, right? As a map from L infinity of omega, right, to L infinity of omega, right? So you just highlight Fréchet differentiable, right, at every point, right? So right, I mean, if you want to prove this, then I mean, you can actually prove that the sine function, right, defined from L infinity of omega to L infinity of omega is Fréchet differentiable at every point, right? So I mean, the proof actually uses the mean value theorem, right? So just need to apply the mean value. So apply the mean value theorem twice, right? Twice would be enough. So I mean, feel free to drop your comment in the section below, right? I mean, if you try it out, I mean, if you face any problem, any difficulties, right, then feel free to reach out to me. Okay, so it is not the case in general that the differentiability of little f, right, implies the differentiability of its associated superposition operator. But fear not, right? I mean, there is a little bit of hope, right, with the upcoming theorem I'm about to state, right, which basically suggests that under mild assumptions, right, that is known as the two-norm discrepancy. So under mild assumption, not only can we achieve differentiability of the superposition operator, capital F, right, but we can also kind of precisely identify its derivative. So this will be our next theorem. So theorem 2.11. Okay, so again, we recall the assumptions. So let f, right, defined from omega. I mean, this is a Caratheodory function, be Caratheodory function that we defined at the very beginning, right, that satisfies the growth condition G, right, for one less or equal than Q strictly less than P, right? Because now we need to have kind of a two-norm discrepancy, right? I mean, the codomain and the domain of the superposition operator should be different, right? So for P between this and this, right? So let me just highlight this, right? So now we can no longer have P equals to Q, right? So this is not a plausible case anymore, right? We also need Caratheodory function. Okay, so now under this assumption, right, if furthermore, right, if I think I need to use another color. So good. So if furthermore the partial derivative, right? Furthermore, the partial derivative f prime of z, f prime, I mean derivative with respect to the variable z, right, of little f, is a Caratheodory function. So if furthermore f prime is a Caratheodory function, right? Partial derivative of f with respect to z is a Caratheodory function as well, and satisfies the growth condition for put it in color for p prime, right, equals p minus q, right? Then the superposition operator, just write it again, right? Then the superposition operator capital F, right, defined from LP of omega into LQ of omega, right, is continuously Fréchet differentiable. Right, and its derivative is Fréchet derivative, right, in U being an element of LP of omega, right, in direction H Oops, let me just write it probably here. Direction H still in LP of omega, right? Is given by probably I use this color. This is f prime of u, right? Apply to H, right? Apply to the point X. So this will be f prime, the partial derivative of f with respect to z, right? At x, comma ux, right? Apply to each at the point X, right? This is for almost every x in omega. Okay, so if you have a Caratheodory function that has that satisfies the growth condition with P and Q being strictly different, right? And if furthermore the partial derivative, right, the partial derivative of your Caratheodory function, right, with respect to the second variable is the Caratheodory function itself, right, and satisfies also the growth condition with P prime equal to P minus Q, then the superposition operator of your original function little f, right, is continuously free-shade differentiable, right, and you can even characterize its free-shade derivative this way. Okay, so let's go into the proof, right, which is not so difficult. So proof. Okay, now since f prime of z, right, is a Caratheodory function, it's a Caratheodory function. This is by assumption, right? That satisfies by f prime of z, the partial derivative of f, right, with respect to z. So don't get confused. So since f prime of z is a Caratheodory function that satisfies the growth condition G, right, that we defined at the very beginning for P prime equals P minus Q, right? So let me just probably recall what this growth condition will be. So this means that f prime of z, right, at x comma u of x, right, you can even put whatever you want there. So this means that's equal than a of x, right, plus b of x times the absolute value of u of x, right, to the power p prime over q, right, with a being a function in LQ that exists, right, by definition of the growth condition, and p is in L infinity. Okay, so because f prime of z satisfies the growth condition, is a Caratheodory function, it follows from theorem 2.10, right, that we just proved. So it follows from theorem 2.10. Let me just highlight. So it follows from that theorem that I think this looks ugly. So it follows that for now we choose a specific the specific a specific R, right, for which we can construct a very nice superposition operator. So it follows from theorem 2.10 that for R equal P times Q, right, divided by P minus Q, right, so this basically means that P minus Q, right, over Q is equal to P over R, right, and this means that P minus Q was actually P prime, right? This is how we define it. We set P minus Q to be P prime, so this is equal to P over R. So it follows that for this particular choice of R, right, the superposition operator of our partial derivative, right, of the partial derivative of f with respect to z, which is a Caratheodory function. For the superposition operator, we call it capital G, right, defined from Lp of omega into Lr of omega, right? Full expression is gu of x, right? gu of x is equal to partial derivative of f with respect to z, right, at the point x, ux, for, of course, for almost every x into omega. So it follows that this superposition operator is well defined. It's well defined and continuous, right? And continuous. Okay. So this is well defined and continuous. Also, the Hölder inequality. The Hölder inequality. I mean, here we are going to use the generalized Hölder inequality. Right? So the Hölder inequality, right? Further, implies that for every u, right, in Lp of omega, the norm of du applied to h, right, in Lq of omega, right, this is less or equal than, I mean, the Lq norm of this is actually less or equal than the norm of du in Lr, right, oops, times the norm of h in Lp of omega. I mean, observe that, I mean, this is an element of Lr, right, by definition of the superposition operator, and this h is actually in Lp of omega. This is a direction. So, and if you check it, I mean, if you make the computation, then you see that 1 over r plus 1 over p, right, is equal to 1 over q, right? So this means that this product here is actually in LQ, and then by the generalized order, it is less equal than the R norm of GU times the P norm of H, right? Of course, so this is less equal than this for every H in LP of omega, right? So with this, we basically prove that the maps which at H associate GU applied to H, right, defines, this map actually defines a bounded, bounded linear operator, right? Bounded linear operator that we call DFU, right? This will be our Frischer derivative, right, of our superposition operator F applied to U, which is defined from LP of omega into LQ of omega, right? LQ of omega, because we saw that this is in LQ. Oops. Right, we saw that this was actually in LQ, right? So this map actually defines a linear bounded operator, DFU, right? Defined from LP of omega to LQ of omega. Now, to finish or to conclude right now, let's prove that f prime of u, right, applied to h, right, is exactly the f of u, right, applied to h, which is b of u applied to h. So now let's prove that this holds, right? So because of this, we'll be able to conclude, right, that our function superposition operator f is continuously differentiable, and that its Fréchet derivative is exactly the, what we define it to be, right, in the theorem. Okay, so let H, right, so the element elliptic of omega, right, be arbitrary. Since the map which at z associate f of x comma z is continuous, right? It's even continuously differentiable. Since this map is continuously differentiable, because we saw that you have the assumption that the partial derivative with respect to z exists, and we also know that it is also a Caratheodory function, right? So it is continuously differentiable. So since this map is continuously differentiable, the assumption, right? This is by assumption. Right, the classical mean value theorem implies the classical mean value theorem. Just highlight. It's a very crucial property that we're going to use here. So the classical mean value theorem implies that the norm of f of u plus h, right, minus f of u minus this applied to h, right, the LQ norm of this. So the goal is to show that this is actually little o of norm of h, right? Because this is basically the definition of Fréchet differential, right? So this is equal to now you're just going to be something about replacing things, right? So this is equal to the integral of omega, right, of the absolute value of f of x comma ux, right, plus h of x. It's only about replacing things, right? Minus f of x comma ux, right, minus f prime of z, f prime, the partial derivative of f with respect to z, at the point x comma ux, right, applied to to h of x, right, this to the power q dx, and everything to the power 1 over q. This is the LQ norm, right, by definition. Now the mean value property basically says that this is equal to the integral of omega, right, of the absolute value of the integral from 0 to 1. I will explain what I'm doing or what is going through very soon, plus t hx, right, applied to hx. Let me just bring it a bit to the other side. Okay, let's go to this times dt minus f prime z at x applied to ux, oops, h of x to the power q dx, everything to the power 1 over q. And then I said that this equality follows from the mean value property. I will just write MVP, right? Not for the most valued person, right, or the MVP in NBA, right? This is to mean the mean value property, MVP. Okay, so I apply the mean value property with this term here, these two terms here. So the mean value property basically says that this is equal to the integration of this, right? So that is basically it, right? So okay, well, now what you need to observe is that this is again equal to the norm, right, of the integral from 0 to 1 of, which can actually the norm of the integral from 0 to 1 of g of u plus th, right, applied to h dt. This is just simply by definition, right? Nothing. I just replace f prime of z at x, comma ux plus th of x times h of x by g of u plus th, right? Applied to h gt, right? Minus. This is only about replacing things by their value, right? Times h. Yeah. So this is the norm of this, right? In LQ. Wait. Yeah. Now observe that this observe that this term here, you can even bring it inside the integration over the dt, right? You can bring it inside because it doesn't depend on t, and the integral from 0 to 1 is 1, so you can put it inside. So put it inside the integral, right, as the integral from 0 to 1 dt is equal to 1. So if you put it inside, right, and then use triangle inequality, so this is just equal to the integral from 0 to 1, right, yes, of the norm of g of u plus th, right, minus g of u, everything applied to h, the norm of this in LQ dt. And now here you use Hölder inequality once again, right, because you have a kind of a product, right? Here you use Hölder. So this is less equal than the integral from 0 to 1 of the norm of du plus th minus du, right? This is the LR norm of this dt, right, times the norm of h in LP, right? Yeah. Now, I think we are basically done, right? Now observe that this term here, right, actually goes to 0, right, as the norm of h, right, in LP of omega goes to 0, right, since, this is because J is continuous. Okay, so because of that, we have that the norm of f of u plus h, right, minus f of u minus dfu of h, right, in LQ, yes, this is equal to little o of norm of h in LP, right, for norm of h in LP, in LP of omega, right, going to 0. So hence, f is Fréchet differentiable, and f prime of u, the Fréchet derivative at the point u, is exactly the f of u, right? And of course, we prove already that this Fréchet derivative is continuous, right? So Rowe's continuity has been proven. Already. So you can pause the video and probably go back if you want, right? If I will prove that the map widget h associate du of h, right, is continuous, right? saw that it was a linear bounded operator, right? So it's continuous. Okay, so let me just correct this part here. Nice. So this is actually the end of the proof, right? And I mean, yeah, I mean, this is a rather sharp result, right? So let's have a remark, right? So let's have a closing remark. So except for the case P equal Q equal plus infinity, let me just highlight except, right? For this case, right? Let me use another color. Yeah, no superposition operator. So except for this case, for the case where P and Q equal to plus infinity, no superposition operator. No superposition operator is differentiable, right? From LP into LP. Is differentiable from LP of omega, right, to LP of omega, right? Unless, of course, unless use another color, yeah. Unless it is affine, right? I mean, if you have affine functionals, I mean, they are really nice functions, so everything is smooth. So no superposition operator, right? Except for the case P equal to Q equal to plus infinity, the superposition operator is differentiable, right? I mean, the case P equal to Q equal to infinity is actually excluded because we saw that at the very beginning that the map, just write it probably, we saw that the map, right, Richard U associate sign of U, right, is Fréchet differentiable, right? I said you can prove it using the mean value theorem, right? Apply the mean value property twice. So it's Fréchet differentiable. Omega infinity of omega, right? Yeah. So again, I strongly invite you to prove it, right? So, okay, so this was well, quite lengthy video, right? So I hope you enjoy it. So feel free to leave your comment in the session and also leave a thumbs up, right, if you enjoyed the video. So see you in the next video, and until then, stay hungry, stay foolish, and yeah, stay curious.